Hello everyone, welcome to this YouTube channel, MathSense. This is the second lecture of series solution of ordinary differential equation. In previous lecture, we discussed some definition which will be useful in finding series solution. We also know in that lecture that there are two different methods to find series solution. First one is power method and the second one is Frobenius method. So here in this lecture, we are going to discuss power method. Power method means solution about ordinary point. So let p0 of x d square y by dx square plus p1 of x into dy by dx plus p2 of x into y that equals to 0. This is equation 1. This equation looks familiar because we discussed about it in first lecture. Now, if x equal to a is an ordinary point of the differential equation 1, then its every solution can be expressed in the form y is equal to summation n running from 0 to infinity an into x minus a whole raised to n. That equal to a0 plus a1 into x minus a plus a2 into x minus a whole square plus a3 into x minus a whole cube plus so on. This is equation number 4. So in power method, you can write the solution in this summation notation, or you can use this expanded version of series where the power series converges in some interval modulus of x minus a less than capital R about a. Thus, the series may be differentiated term by term on this interval, and we have. Now, we are going to differentiate this entire series with respect to x. So, here, derivative of y with respect to x, we can write it as a dy by dx, and derivative of this entire term an into x minus a whole raised to n with respect to x is n an x minus a whole raised to n minus 1. So you can write this differentiation of this summation, entire summation notation like n running from summation n running from 1 to infinity n an x minus a whole raised to n minus 1. Here you can see we have a0. So derivative of a0 is 0. Same for the next term. Derivative of a1 into x minus a is a1. Derivative of a2 into x minus a whole square is 2a2 into x minus a. Derivative of a3 into x minus a whole cube is 3 into a3 x minus a whole square. So you can write the entire differentiation of the series as dy by dx that equal to summation n running from 1 to infinity n an x minus a whole raised to n minus 1 that equal to a1 plus 2a2 into x minus a plus 3a3 into x minus a whole square plus so on. That is equation number 5. Now differentiate this entire term with respect to x one more time. So we get d square y by dx square. So that equal to summation n running from 2 to infinity into n into n minus 1 an x minus a whole raised to n minus 2. Or that equal to 2a2 plus 6a3 into x minus a plus 12a4 into x minus a whole square plus so on. This is equation number 6. So here you can observe this change. So when we are differentiating this term first time, so summation's range will be 1 to infinity, and when we are differentiating this term one more time, so summation range will be 2 to infinity. Now substituting the values of y dy by dx and d square by dx square in equation 1, we get an equation of the type c0 plus c1 into x minus a plus c2 into x minus a whole square plus so on that equals to 0. This is equation number 7. So in this equation 1, we substitute y double dash, y dash and y, then after some simplification, we get this type of equation, and that is equation number 7, where the coefficients c0, c1, c2 and so on are functions of a. The equation 7 will be valid for all x in modulus of x minus a less than capital R if all c0, c1, c2 and so on are zeros. So that means C0 that equals to C1 that equals to C2 that equals to so on, and that equals to 0. This is equation number 8. So here basically in equation number 7 we are comparing this coefficient C0, C1, C2 and so on with the 0, and after solving this relation we can find value of the coefficient AI of equation 4. So the coefficients AI of equation 4 are obtained from the equation 8. In case equation 7 is expressed in power of x, then equating to 0 the coefficient of the various power of x will determine a2, a3, a4 and so on in terms of a0 and a1. The relation obtained by equating to 0 the coefficient of x raised to n is called the recurrence relation. Now in this entire process the recurrence relations are very important, because by using that we can find the other coefficients AI. Now we can see how it works, how this method works with the example. So first example is find the series solution of y dash minus 2xy that equals to 0. So here we have first order differential equation, and instruction is very simple, that find the series solution. No additional information is given here. So let's begin with the given thing. So here y dash minus 2xy that equals to 0. This is equation 1. Comparing it with p0 of x dy by dx plus p1 of x into y that equals to 0. So we have p0 of x that equal to 1, p1 of x that equals to minus 2x. Now here we can see p0 of x equals to 1, which is not equals to 0 for all x belongs to R. That means all x belongs to R are ordinary points of equation 1. So this equation 1, that given equation, doesn't have any singular point. So we can choose any point from this entire set of real number, and we can find solution by using power method. You can choose x equal to 0, you can choose x equal to 1, you can choose x equal to minus 1, you can choose x equal to 100, you can choose x equal to minus 100 also, any number, any real number. But for simplicity we choose x equal to 0. So let x equal to 0 is an ordinary point of equation 1. So in the beginning we see x equal to a. So in this theory we have a, and in that example we find value of a, that is 0. So let x equals to 0 is an ordinary point of equation 1. So series solution of equation 1 about x equal to 0 is y is equal to summation n running from 0 to infinity an into x minus 0 whole raised to n. If you choose x equal to 1 here, so we get x minus 1. If you choose x equal to minus 1 here, so we get x minus minus 1 whole raised to n. That means x plus 1 whole raised to n. So it depends on the point. So that equal to summation n running from 0 to infinity an into x raised to n. Or you can write in descriptive form, that is a0 plus a1 x plus a2 x square plus so on. This is equation 2. Now differentiate this series with respect to x. So we get y dash that equals to summation n running from 1 to infinity. Derivative of this term is n x raised to n minus 1. Or you can write a1 plus 2a2x plus so on. Now substituting these values in equation 1 we get, so y dash equals to summation n running from 1 to infinity n x raised to n minus 1, and y is equal to summation n running from 0 to infinity x raised to n. Substituting this value we get summation n running from 1 to infinity n x raised to n minus 1 minus 2x into summation n running from 0 to infinity x raised to n, and that equals to 0. Now we are going to include this 2x in this summation. So we get, so first summation will be as it is, summation n running from 1 to infinity n x raised to n minus 1 minus summation n running from 0 to infinity to an x raised to n plus 1, that equals to 0. Now here we have two different summation. We want to merge this two summation, but problem is that the range of summations are different and the power of x are different. So right now we can't merge these two summations. So first we try to make this power of x common. So to obtain common power of x in each term, replace n by n minus 2 in the second term. So here we are going to replace n with n minus 2 in second summation. First summation remains as it is. So summation n running from 1 to infinity n an x raised to n minus 1 minus summation n running from 2 to infinity 2a n minus 2 into x raised to n minus 1, that equals to 0. Now here you can see the power of x are same now, but the range of summation is still different. So in first summation we have 1 to infinity, and in second summation here we have 2 to infinity. So now let's represent this first summation in a different form. So we put n is equal to 1 here, so we get 1 into a1 x raised to 0, and we write the other term in the form of summation notation. So we get a1 plus summation n running from 2 to infinity n an x raised to n minus 1 minus the next summation will be as it is. So summation n running from 2 to infinity 2a n minus 2 x raised to n minus 1, and that equals to 0. Now you can observe the power of x are same, the range of summation are same. So now we can merge these two summations. So a1 will be as it is plus summation n running from 2 to infinity in a bracket n an minus 2a n minus 2 into x raised to n minus 1. After this stage, equating to 0 the coefficient of x raised to 0 and x raised to n minus 1, where n is greater or equal to 2, we get. So now we are equating this coefficient of x raised to 0. So here on the left hand side the coefficient of x raised to 0 is a1, and on the right hand side the coefficient of x raised to 0 is 0. So equating a1 is equal to 0. So we get value of a1, that is 0. Now here coefficient of x raised to n minus 1 is n an minus 2 an minus 2, and on the right hand side the coefficient of x raised to n minus 1 is 0. So equating this coefficient with 0 we get n an minus 2 an minus 2, that equals to 0, where n is greater or equal to 2. Now simplify this equation, we get n an that equals to 2 an minus 2, where n is greater or equal to, and finally we have an is equal to 2an minus 2 divided by n, where n is greater or equal to 2. This is known as recurrence relation. So that means that part is very important here. We can find other coefficients by using this relation. So putting n is equal to 2, 3, 4 and so on. So if we put n is equal to 2 here, so we get a2, and that equal to 2a0 divided by 2. So finally we have a2 is equal to a0. Now if we put n is equal to 3 here, so we get a3 is equal to 2a1 divided by 3. So but we find a1 is equal to 0. So we get a3 is equal to 0. Now if we put n is equal to 4 here, so we get a4 that equals to 2a2 divided by 4. So that means that equal to a2 by 2. But we know a2 is equal to a0. So after substituting the value of a2, we get a4 is equal to a0 by 2. And so on, we can find the other coefficients. Now substituting all this new value in equation 2, we get, so equation 2 is actually y is equal to a0 plus a1 into x plus a2 into x square plus a3 into x cube plus a4 into x raised to 4 and so on. So a0 will be as it is, value of a1 is 0, value of a2 is equal to a0, value of a3 is 0, value of a4 is a0 by 2. So after substituting we get y that equal to a0 plus 0 into x plus a0 into x square plus 0 into x cube plus a0 by 2 into x raised to 4 plus so on. So we get y is equal to a0 plus a0 into x square plus a0 by 2 into x raised to 4 plus so on. So final answer will be y is equal to a0 in a bracket 1 plus x square plus x raised to 4 divided by 2 factorial plus so on. So this is the series solution of given differential equation. You can write this solution as y is equal to a0 into e raised to x square, because you can see this is a Maclaurin series of x square also. Now let's understand this process with another example. So example 2 is find the power series solution of d square y by dx square plus y that equals to 0 about x0 is equal to 0. So in first example the instruction is very simple, that simply they ask find the series solution. Here with this information, with given differential equation, there is one other information, and that is the point is given, and that is here x0 is equal to 0. So here they clearly mention that we need to find solution of this differential equation at point x0 is equal to 0. If this point is ordinary point, so we can use power method. If this given point is singular point, we can use Frobenius method. So let's begin with the given information. So here d square y by dx square plus y that equals to 0 and x0 equals to 0. Now you can write this equation as y double dash plus y that equals to 0. This is equation 1. Now comparing with p0 of x d square y by dx square plus p1 of x dy by dx plus p2 of x into y that equals to 0. So here p0 of x that equal to 1, p1 of x that equals to 0 and p2 of x that equals to 1. So you can see p0 of x that equal to 1, which is not equal to 0 for all x belongs to R. So that means all x belongs to R are ordinary points of equation 1. So here that given point x0 equals to 0 is an ordinary point of equation 1. So we need to find solution at ordinary point. That means we can apply power methods. So let's series solution of equation 1 about x equals to 0 is y is equal to summation n running from 0 to infinity an x minus 0 whole raised to n, that equal to n running from 0 to infinity an x raised to n. You can write that equal to a0 plus a1x plus a2x square plus a3 into x cube plus so on. That is equation number 2. Now I mentioned it before, you can write this series solution in the form of summation, or you can write in this form of series. Only use any one form, no need to mention both. So after differentiating one time we get y dash is equal to summation n running from 1 to infinity n an x raised to n minus 1, or you can write that equal to a1 plus 2a2x plus 3a3x square plus so on, and y double dash that equal to summation n running from 2 to infinity n into n minus 1 an x raised to n minus 2, that equal to 2a2 plus 6a3x plus so on. Now substitute all this value in equation 1. So we get summation n running from 2 to infinity n into n minus 1 an x raised to n minus 2 plus summation n running from 0 to infinity an x raised to n, that equals to 0. Now here again we want to merge this 2 summation, but problem is same. The range of summations are different and the power of x are different. So again, to obtain common power of x in each term, replace n by n plus 2 in the first term. So here we are going to change, we are making that replacement in first summation. So second summation will be as it is. So replace n by n plus 2. Here we get summation n running from 0 to infinity, n plus 2 into n plus 1, a n plus 2 x raised to n, plus summation n running from 0 to infinity, a n x raised to n, that equals to 0. Luckily here we get common range of summation. So now we can merge this two summation. So after merging them, we get summation n running from 0 to infinity in a bracket n plus 2 into n plus 1 into a n plus 2 plus a n bracket complete x raised to n, that equals to 0. Equating the coefficients of x raised to n, where n is greater or equal to 0, we get, so n plus 2 into n plus 1 a n plus 2 plus a n, that equals to 0, where n greater or equal to 0. So after simplification we get n plus 2 into n plus 1 a n plus 2, and that equals to minus a n, where n is greater or equal to 0. So that means a n plus 2, that equals to minus a n divided by n plus 2 into n plus 1, where n is greater or equal to 0. Now putting n is equal to 0, 1, 2 and so on. So if we put n is equal to 0 here, we get a2, that equals to minus a0 divided by 2 into 1. So we can write this equal to minus a0 divided by 2 factorial. If you put n is equal to 1 here, we get a3, that equals to minus a1. Here we have 3 into 2. So you can write that equals to minus a1 divided by 3 factorial. Now if we put n is equal to 2, so we get a4, that equals to minus a2, and in denominator we get 4 into 3. So we have a4 is equal to minus a2 divided by 4 into 3. But we know a2 is equal to minus a0 by 2 factorial. So after substituting that value, we get a0 divided by 4 into 3 into 2 factorial, or you can write it as a0 divided by 4 factorial. So value of a4 is a0 divided by 4 factorial. Now if we put n is equal to 3 here, so we have a5 is equal to minus a3 divided by 5 into 4, and after substituting value of a3, we get a1 divided by 5 into 4 into 3 factorial. So that means a5 is equal to a1 divided by 5 factorial. And continuing this way, we can find other coefficients, so on. Now substituting this in equation 2. So equation 2 is y is equal to a0 plus a1 into x plus a2 into x square plus a3 into x cube plus a4 into x raised to 4 plus a5 into x raised to 5 plus so on. So a0 is as it is, a1 is as it is, value of a2 is minus a0 divided by 2 factorial, value of a3 is minus a1 divided by 3 factorial, value of a4 is a0 divided by 4 factorial, value of a5 is equal to a1 divided by 5 factorial, and so on. So after substituting this value, we get y, that equal to a0 plus a1x minus a0 divided by 2 factorial into x square minus a1 divided by 3 factorial into x cube plus a0 divided by 4 factorial into x raised to 4 plus a1 divided by 5 factorial into x raised to 5, and so on. So here you can observe we have terms which contain a0 and we have terms which contain a1. So after separation we get y is equal to a0 in a bracket 1 minus x square by 2 factorial plus x raised to 4 by 4 factorial minus so on, plus a1 is equal to a1 into x minus x cube by 3 factorial plus x raised to 5 by 5 factorial minus so on. So this is the power series solution of given differential equation. Now further, you can write it. This is a Maclaurin series of cos function, and this is a Maclaurin series of sine function. So you can write it as y is equal to a0 cos x plus a1 sin x also. But if you don't remember this Maclaurin series, then you can simply write this as a solution. So now let's discuss the one more example regarding this. So example number 3 is using the power series solution solve 1 minus x square into y double dash minus 2xy dash plus 2y that equals to 0. So here they specify the method by using power series method only. Find the solution of this differential equation. So here the given equation is 1 minus x square into y double dash minus 2xy dash plus 2y that equals to 0. This is equation 1. Comparing with p0 of x d square y by dx square plus p1 of x dy by dx plus p2 of x into y that equals to 0. So we get p0 of x equal to 1 minus x square, p1 of x that equals to minus 2x, and p2 of x that equals to 2. So at singular point we know p0 of x equals to 0, but here p0 of x equal to 1 minus x square. So we can equate this with 0, so 1 minus x square that equals to 0. So value of x, so we get x equal to plus or minus 1. That means x equal to plus or minus 1 are singular points, and all other points, that means except this plus 1 and minus 1, all other real numbers are ordinary point. So it is clear that x equals to 0 is an ordinary point of equation 1. So we can find solution at x equals to 0. So let series solution of equation 1 about x equal to 0 is y is equal to summation n running from 0 to infinity an x minus 0 whole raised to n. This is equation number 2. Now differentiate this term with respect to x. One time we get y dash that equal to summation n running from 1 to infinity n x raised to n minus 1. And one more time we get y double dash that equal to summation n running from 2 to infinity n into n minus 1 x raised to n minus 2. Now substituting all this value in given equation 1, we get, so 1 minus x square will be as it is. Value of y double dash is summation n running from 2 to infinity n into n minus 1 x raised to n minus 2 minus 2x, and value of y dash is summation n running from 1 to infinity n x raised to n minus 1 plus 2 into summation value of y is summation n running from 0 to infinity x raised to n that equals to 0. So here we multiply this 1 with summation, so we get 1 into this summation, that is summation n running from 2 to infinity n into n minus 1 minus x raised to n minus 2 minus x square into this summation, so minus x square into summation n running from 2 to infinity n into n minus 1 x raised to n minus 2 minus, we are going to include this 2x into this summation, so we get summation n running from 1 to infinity 2n x raised to n here. And again in the next summation we are going to include this 2 into this summation notation. We get summation n running from 0 to infinity 2 x raised to n, and that equals to 0. So first summation will be as it is, summation n running from 2 to infinity n into n minus 1 x raised to n minus 2. Now include this x square into this summation notation. We get summation n running from 2 to infinity n into n minus 1 x raised to n minus summation n running from 1 to infinity 2n x raised to n, and summation n running from 0 to infinity 2an x raised to n, and that equals to 0. So in this example, we have 1, 2, 3, 4, 4 different summation notation, and we want to merge all 4. So let's check. The range of summations are different, yes, and the power of x are also different. So first, to obtain common power of x in each term. So in first summation, it is x raised to n minus 2. But in second, third, and fourth, we have x raised to n. So we are going to change in first summation. So to obtain common power of x in each term, replace n by n plus 2 in the first term. So other 3 summations are will be as it is. So in first summation, replace n by n plus 2. So we get n running from 0 to infinity, n plus 2 into n plus 1, a n plus 2 x raised to n, minus summation n running from 2 to infinity, n into n minus 1 into a n x raised to n, minus summation n running from 1 to infinity 2n a n x raised to n, plus summation n running from 0 to infinity 2an x raised to n, that equals to 0. Now here you can observe power of x are common, but again the range of summations are different. So let's make them same. So we represent first summation in a different way. So we are going to put n is equal to 0 and n is equal to 1, and after that we are going to write the other values. So 2, 3, 4 and up to infinity, other value in a summation notation. So if we put n is equal to 0 here, we get 2 into 1 into a2 x raised to 0. So if we put n is equal to 0, we get 2a2. Now if we put n is equal to 1, so we have 3 into 2, that means 6, and a3 into x raised to 1. So if we put n is equal to 1 here, we get 6a3 into x, and other terms are going to represent in a summation notation. So summation n running from 2 to infinity, n plus 2 into n plus 1, a n plus 2 x raised to n. So the second summation notation here will be as it is, summation n running from 2 to infinity n into n minus 1 a n x raised to n. Now in third summation, we put n is equal to 1, and we are going to write the other terms into summation notation. So if we put n is equal to 1 here, we get 2 into 1, that is 2, into a1 into x. So if we put n is equal to 1 here, we get minus 2a1 into x, minus the other term will be in a summation notation. So 2 to infinity, summation 2 to infinity 2n an x raised to n, and same for the last summation. So here we are going to put n is equal to 0 and n is equal to 1, and after that we are going to write the other term in summation notation. So if we put n is equal to 0 here, we get 2 a0 x raised to 0. That means if we substitute n is equal to 0 there, so we get 2a0. Now same if we put n is equal to 1 here, so we get 2 into a1 into x. So if we put n is equal to 1, we get 2a1x, and other term will be in a summation notation. So summation n running from 2 to infinity 2an x raised to n, and that equals to 0. So actually we did this entire process to make the summation range 2 to infinity in a summation notation. So here now we are going to write this separate terms first. So 2a2, 2a0, 2a1x plus 6a3 minus 2a1x plus, now here we have 4 different summation and we can merge them because power of x are common, range of summations are same. So after merging all this 4 summation, we get summation n running from 2 to infinity in a bracket n plus 2 into n plus 1 a n plus 2 minus n into n minus 1 a n minus 2an into n plus 2an bracket complete x raised to n, that equals to 0. So here you can see we have plus 2a1x and minus 2a1x. So after simplification we get 2a2 plus 2a0, and we have one single term which contain x. So 2a2 plus 2a0 bracket complete plus 6a3 into x plus summation n running from 2 to infinity n plus 2 n plus 1 an plus 2 minus n into n minus 1 an minus 2n an plus 2an bracket complete x raised to n, that equals to 0. Now equating the 0, the coefficient of x raised to 0, x and x raised to n, where n is greater or equal to 2, we get. So first equating the coefficient of x raised to 0, and it is 2a2 plus 2a0, that equals to 0. So we get a2 is equal to minus a0. Now equating coefficient of x, that is 6a3 with 0. So 6a3 is equal to 0, that means a3 is equal to 0. And after that, equating the coefficient of x raised to n, and that is n plus 2 into n plus 1 into an plus 2 minus n into n minus 1 into an minus 2n into an plus 2an, that equals to 0, where n is greater or equal to 2. So here let's simplify this. So we get n plus 2 into n plus 1 an plus 2 minus n square. After simplify this, we get n square minus n minus 2n, plus 2n minus 2 bracket complete an, that equals to 0, where n is greater or equal to 2. So here we have n plus 2 into n plus 1 an plus 2 minus n square plus n minus 2 bracket over an, and that equals to 0, where n is greater or equal to 2. So we get an plus 2, that equal to n square plus n minus 2 into an divided by n plus 2 into n plus 1. So here you can see factors of this n square plus n minus 2 are n minus 1 and n plus 2. So we have an plus 2, that equal to n minus 1 into n plus 2 into an divided by n plus 2 divided by into n plus 1. So we have n plus 2 in numerator and n plus 2 in denominator. So after cancellation, finally we have an plus 2, that equal to n minus 1 divided by n plus 1 into an, where n is greater or equal to 2. Now this is a recurrence relation. So putting n is equal to 2, 3, 4 and so on, we get, if you put n is equal to 2 here, we get a4, that equal to 1 by 3 into a2. But here we find a2 is equal to minus a0. So after substituting that value, we get a4 is equal to minus a0 by 3. Now if we put n is equal to 3 here, we get a5, that equal to 2 by 4 into a3. But we know value of a3 is 0. So after substituting that value, we get a5 is equal to 0. Now if we put n is equal to 4 here, we get a6 is equal to 3 by 5 into a4. But value of a4 is minus a0 by 3. So after substituting that value, we get a6 is equal to minus a0 by 5. And so on. Continuing in this way, we can find other coefficients. Now substituting all this value in equation 2, we get, so equation 2 is actually y is equal to a0 plus a1x plus a2x square plus a3x cube plus a4x raised to 4 plus a5x raised to 5 plus a6x raised to 6 and so on. So y is equal to a0 will be as it is, a1 will be as it is. Now value of a2 is minus a0, value of a3 is 0, value of a4 is minus a0 by 3, value of a5 that equals to 0, value of a6 is minus a0 by 5. So after substituting all this value, we get y is equal to a0 plus a1x minus a0 x square minus a0 by 3 x raised to 4 minus a0 by 5 x raised to 6 and so on. So here we have only one term which contain a1 and all other term contains a0. So you can write y is equal to a1 into x plus a0 into 1 minus x square minus x raised to 4 by 3 minus x raised to 6 by 5 and so on. So this is the series solution of given differential equation. So this is all about, this entire lecture is all about power method. I hope you understand it well. So practice some extra example regarding this, and thank you. Keep practicing.